Welcome to Automotive Basic Knowledge. Now our topic is about automotive CAN bus system. In this discussion we covered controller area network system, CAN bus output signal, CAN bus components, CAN data transfer process, CAN bus data message structure, how the CAN system works. Controller area network system. The controller area network, CAN, also known as CAN bus, is a vehicle bus standard designed to allow electronic control units and devices to communicate with each other and applications without a host computer. As an alternative to conventional multi-wire looms, CAN bus allows various electronic components, such as electronic control units, microcontrollers, devices, sensors, actuators and other electronic components throughout the vehicle, to communicate on a single or dual-wire network data bus up to 1 megabit per second. The CAN bus is a message-based protocol, designed originally for multiplex electrical wiring within motor vehicles, but also can be used in many other contexts. Figure 1 shows a simplified schematic diagram of the CAN system and shows some of the possible units, devices that can be connected onto the CAN bus. CAN bus output signal. Typically the CAN bus is made up two wires, CAN H and CAN L, which connect to all the devices in the network. The signals on the two CAN lines have the same sequence of data, but their amplitudes are opposite. So if a pulse on the CAN H line goes from 2.5 volts to 3.75 volts, then the corresponding pulse on the CAN L line goes from 2.5 volts to 1.25 volts, opposite than CAN H. By sending the data in equal and opposite ways like this allows for greater noise immunity and therefore less chance of the data being corrupted. Figure 2 shows CAN H and CAN L differential output. Status of bit with the value 0 equals 2.5 volts differential voltage equals dominant state. Status of bit with the value 1 equals 0 volts differential voltage equals recessive state. CAN bus components. Figure 3 shows an example of two connected devices as well as the components that make up a CAN bus, CAN controller, CAN transceiver, two data bus terminals, R, and two data bus lines, CAN high line and CAN low line. Figure 3 shows CAN bus components. CAN controller receives the transfer data from the microcomputer integrated in the control unit, device, also known as CAN node. The CAN controller processes this data and relays it to the CAN transceiver. Also, the CAN controller receives data from the CAN transceiver, processes it and relays it to the microcomputer integrated in the control unit, device, CAN node. CAN transceiver is a transmitter and receiver in one. It converts the data which the CAN controller supplies into electrical signals and sends this data over the data bus lines. Also, it receives data and converts this data for the CAN controller. CAN data bus terminal is a resistor, R, typically of 120 ohms. It prevents data sent from being reflected at the ends and returning as an echo. CAN data transfer process. The CAN data transfer process consists of the following stages: supplying data, sending data, receiving data, checking data and accepting data. Figure 4 shows CAN bus data transfer process. Supplying data, the CAN node provides data to the CAN controller for transfer. Sending data, the CAN transceiver receives data from the CAN controller, converts it into electrical signals and sends them back into the network. Receiving data, all other CAN nodes networked with the CAN data bus become receivers. Checking data, the CAN node checks whether they require the data they have received for their functions or not. Accepting data, if the received data is important, it is accepted and processed. If not, the received data is ignored. There are two different ISO standards for CAN systems that relate to the physical layer: ISO 11898 3 low speed CAN up to 125 kilobits per second, distance up to 500 meters, and ISO 11898 2 high speed CAN up to 1 megabit per second, distance up to 40 meters. The CAN system is further divided into two formats for the message frames: 2.0a and 2.0b. The two standards differ in the size of the identifiers, ID. Standard CAN, Version 2.0a uses 11-bit identifiers in the arbitration field. Extended CAN, version 2.0b, supports a length of 29 bits for the identifier, made up of the 11-bit identifier, base identifier, and an 18-bit extension. CAN bus data message structure. Figure 5 shows the CAN bus data message structure. The basic structure of the message is the same for both standard and extended version. Figure 5 shows CAN bus data message structure. SF equals start field indicates the beginning of a message with a dominant bit. So this field marks the start of the data protocol. A bit with 3.75 V, depending on the used system, is sent over the CAN H line, and a bit with 1.25 V is sent over the CAN L line, that is, the differential voltage is 2.5 volts, see figure 2. Message identifier defines the level of priority of the data protocol. If, for instance, two CAN nodes want to send their data protocol simultaneously, the CAN node with the higher priority takes precedence. The lower the value, the higher the priority of the message. As stated earlier, depending on the standard being used, the length of the frames can be in two formats: standard, which uses an 11-bit arbitration ID, and extended, which uses a 29-bit arbitration ID. Control, also known as check field, displays the number of items of information contained in the data field. This field allows any receiver to check whether it has received all the information transferred to it. Data field, in this field the information is transferred to the other CAN nodes. CRC equals cyclic redundancy check, also known as safety field, contains 15-bit cyclic redundancy check code and a recessive delimiter bit. The CRC field is used for transfer faults detection. ACK equals acknowledge field, also known as confirmation field. In this field the receivers signal to the transmitter that they have correctly received the data protocol. If an error is detected, the receivers notify the transmitter of this immediately. The transmitter then sends the data protocol again. F equals end field, this field marks the end of the data protocol. This is the last possibility to indicate errors which lead to a repeat transfer. Summary of how the CAN system works. As stated earlier, at the CAN system there is no master that controls when individual CAN nodes have access to read and write data on the CAN bus. When a CAN node is ready to transmit data, it checks to see if the bus is busy and then simply writes a CAN frame message onto the network. The CAN frames that are transmitted do not contain addresses of either the transmitting node or any of the intended receiving nodes. Instead, an arbitration ID that is unique throughout the network labels the frame. All CAN nodes on the CAN network receive the CAN frame, and depending on the arbitration ID of that transmitted frame, each CAN node on the network decides whether to accept or ignore the received frame. If multiple CAN nodes try to transmit a message onto the CAN bus at the same time, the node with the highest priority, lowest arbitration ID, automatically gets bus access. Lower priority CAN nodes must wait until the bus becomes available before trying to transmit again. In this way, you can implement CAN networks to ensure deterministic communication among CAN nodes. The table below shows an example of how the information of engine coolant temperature can be transferred with 1, 2 and 3 consecutive bits and respectively 2, 4 and 8 possible variations. The higher the number of bits, the more items of information can be transferred. The number of possible items of information doubles with each additional bit. If you enjoyed reading and watching this video, please let me know. Click the like button or provide your comment below. Thank you.